Hello, V. Anton Sproul here again to talk about how you can learn to think like a programmer. In this video, I'm going to talk more about code efficiency, and in particular, what I call practical Big O. A quick review is in order. As I've discussed in a previous video, Big O notation is the main way we describe the efficiency of code or an algorithm. That is, how well the code scales based on the problem size. Let's take two sorting algorithms as examples. The selection sort algorithm has a Big O notation of n squared, while the merge sort algorithm has an O notation of n log n. In discussions of algorithm efficiency, n represents the size of the problem, in this case, the number of items we're going to sort. If we plot out various values of n for these two algorithms, we see how much faster merge sort will be than selection sort, especially once the problem size is large. As explained in the previous video, though, this doesn't tell us exactly how much faster merge sort will be compared to selection sort for any particular problem size. And it can even be that the speeds are equal or better for selection sort for very small problem sizes. It does, however, tell us that the larger the problem size gets, the less practical it will be to use selection sort, whereas merge sort can continue to be used even at the largest sizes. When you learn a new algorithm, you'll often be told what the algorithm efficiency is. The question is, how do you determine the efficiency when you're not told? Most likely, this is when you're not following someone else's algorithm, but striking out with your own solution. So how do you determine the Big O notation for code? In most sources on algorithm efficiency, Big O notation is described in precise mathematical terms. And sometimes we do need to deal with efficiency in a precise way. Most of the time, though, we just need to broadly classify an algorithm, function, or other block of code. Is our solution n squared, 2 to the n, n log n, or whatever? That's usually all we need to know because we're just trying to make a basic decision about whether our chosen solution is fast enough for the problem sizes it's going to have to deal with. Or we're trying to choose between multiple solutions for the same problem. Again, we only need to know which one has the better Big O notation. I call this practical Big O, and really it's not that complicated. Let's say that the code we want to analyze is contained within one function. To keep this discussion super simple, for now, let's say that the function doesn't call any other functions except maybe to output results. And let's also say that the function has a parameter called size, and it's this parameter that will change the size of the problem. If we're processing an array in C++, for example, size would be the number of elements in the array. Now, in a language like Python, where the array can tell you its own size, instead of a parameter, we can just say that the first line of the function sets a variable called size to the array size. In any case, the size variable is set before we get to the actual work of the function. Because of how we've defined the problem, in this situation, determining the Big O notation is all about the loops. The for loops, the while loops, whatever kind of looping is available in the language we're programming in. Most loops can be assigned to one of three different categories: Big O1, Big O log n, and Big O n. It's pretty easy to do this, and once we can do that, we're already halfway home. First, let's look at Big O n. The number of times an O of n loop iterates is based on the problem size. In this example, our function is finding the smallest number in the array. Because the number of trips through the loop is determined by the value of the size variable, the amount of work done by this loop is directly proportional to the size of the array. That's Big O of n, linear time. This would be true even if, for example, the number of iterations was equal to half the value of size, as in this example, where we're finding the smallest value that appears in an even-numbered location in the array. Although this loop does half as much work as the previous example for the same value of the size variable, in both cases, the work is proportional to the value of the variable size, and that's all that's important. Next up is big O log n. This kind of loop is going to divide the problem in half during each loop iteration. The most common example of this type of loop is a binary search, which works on an ordered array. In a binary search, we look in the middle location of the array for a particular value, and if we don't find it, we know the value must appear in either the first half or the second half of the array. So for each iteration, we eliminate half of the remaining array until we either find the item we're looking for or we discover it's not there. Because we keep cutting the problem in half, the number of trips through the loop will be equal to the base 2 logarithm of the size of the array. Now, just in case your math is a little rusty on this subject, the logarithm indicates the exponent we have to raise a base to reach a particular number. So the log base A B equals C, well, that just means that A raised to the power of C equals B. In programming, when we say logarithms, it's almost always about dividing a problem in two, so we're pretty much always dealing with a base 2 logarithm. The final type of loop is big O1, or constant time. This is any loop that does not scale with the size of the problem. Here's a cheap example, a function to determine the 8th power of its input. Because this loop always iterates 7 times, no matter what the value of the parameter is, this loop is constant time. Now here's a function that returns the sum of the first 10 values in an array parameter, or fewer than 10 if the array has fewer than 10 items. Now the number of times this loop iterates can be affected by the size of the problem, but because there is a fixed maximum number of iterations, this is a constant time loop. The important thing to remember is, just because you have a loop, it doesn't mean it's proportionally affected by the size of the problem. And if it isn't, or isn't always, then it's just a constant time loop. So, if you have a function that has only one loop, the O notation for that function as a whole is simply the O notation for the loop. But what if you have multiple loops? Well, if your function has 2 or more loops in a row in series, the O notation for the function is just the largest O notation of any of the loops in the function. So just remember that logarithmic time is slower, that is to say its O notation is larger than constant time, and linear time is slower, that is larger, than logarithmic time. Now, we have to remember the difference between performance and efficiency. Of course, if you add a constant time loop to a function that already has a linear time loop, that will slow the function down. But it won't change the efficiency because the function will still scale the same way. In the end, it will be the linear time loop that will decide how fast the function runs once the problem size gets large. Now, if the loops are nested, that is to say one's inside the other, the O notation of the function is the product of the O notation of the individual loops. Here's a function which finds the smallest value in a 2-dimensional array. So here, size, the size variable, is the size of each dimension. Each loop is in itself linear time, a big O n. That means each pass to the outer loop, each pass is big O n work. And that means the total work is order of n times order of n, which is big O n squared. And here's our old friend selection sort. Again, nested loops, and the number of passes of each loop is linearly proportional to the size of the array. Again, the inner loop in a selection sort does less and less work each time we go through it, but that doesn't matter. It's still linear time because if we double the size of the array, we're going to double the amount of work done in the inner loop. So it's a big O n outer loop and a big O n inner loop. So again, big O n squared. And if you've got more deeply nested loops, you just keep multiplying. If you have 3 linear loops nested one inside the other, that's n times n times n, or big O of n cubed. The colloquial word for that is slow. Now, in these examples, all of the code is in one function. If the function calls other functions, we have to consider the O notation of the other functions as well. If you're calling one of the language's library functions, most of the time that will be constant time. You just have to ask yourself whether the work done by that call is affected by the size of the problem. And most of the time it isn't, so that's constant time. But if you make a library call to process an entire data structure, that's when you're going to have to consider the big O time. Some languages have built-in calls to find the largest or smallest value in a data structure, for example. And they pretty much all have built-in sorting. So you use the O notation of the call the same way you would if that was your own code embedded in your function. The C++ sort function, for example, is allowed to vary in its implementation, but it's required to be big O n log n in the worst case. If you called sort and then did your own binary search after that, that would be big O n log n followed by big O log n. And again, the larger term dominates, so that's big O n log n. And that's basically it. That's practical big O. Figure out if your loops are constant time, logarithmic, or linear. Multiply when the loops are nested, and take the largest when they're in a series. And of course, remember to include any function calls in the calculations. That's going to cover the overwhelming majority of situations. The exceptions are problems that are worse than polynomial time, such as exponential time, problems that are big O to the n, for example, which means that increasing the problem size by 1 doubles the amount of work. For example, consider a function that takes the number of bits as a parameter and displays all the binary numbers with that many bits. Increasing the number of bits by 1 doubles the possible binary numbers that are going to have to be output. Problems like these tend to have either recursive solutions or solutions that mimic the effective recursion. And they're going to come up pretty rarely in day-to-day programming. So that's a topic for another day. I hope you enjoyed this video and found it helpful. As always, please like, share, and subscribe. And let me know if you have suggestions for future topics. Thanks for watching.